University of Massachusetts at Amherst, Chemical Engineering, Polymer Science 757, Polymer Rheology, H.H. Winter Lecture 23A. Liquid crystal polymers have a very interesting rheological behavior, and that mostly comes through the self-ordering of the molecules, which by itself then is caused by the molecular structure. Let's talk about the structuring and the order of those liquid crystals before we discuss rheology by itself. And I want to concentrate on pneumatic polymeric systems, which have a special type of order. The molecules can freely move around. They have no positional, they can change their position freely, but they have a directional order. And that's described in the following way. At position X, here we pick a point X, the molecules are locally aligned around a principal direction, and the average direction is called director, and it's given by a unit vector n. The order or the disorder around this vector n is given by the cosine theta, the cosine of the angle theta, which the molecules have with this director. We are averaging this cosine in some special way and define an order parameter. The local director changes when you go to new position. You might have a new director, but the order parameter generally is uniform throughout the sample. There are wall effects where the order parameter is changed, so there might be inhomogeneities in the order parameters. But in most cases, we use a uniform order parameter throughout the bulk of the material. This averaging is done in the following way. Angle theta is defined between molecule and director. This angle has a population density or probability density. There are many molecules around 0, and fewer and fewer molecules as the angle increases. We are integrating now from 0 to pi over all angles, taking cosine square theta and multiplying that with the probability and taking the volume integral, and that's really the definition of cosine square theta, which gives the order parameter. The order comes from the molecular structure, which is changed systematically by the chemist. Here is an example of a very flexible chain, like a polyethylene chain. But if you put in some aromatic groups, or if you have some here this CO double bond group, NH groups, the amine unit, then you obtain some molecular stiffness. And if you have some even further elaborate molecular structure, then the molecule cannot bend at all. It will be completely stiff. Those molecules are semi-flexible. However, the semi-flexible molecules in groups, when they bundle up, increase their stiffness, and they are really acting as solid-like behavior. So the chemistry determines the molecular stiffness, and the flexibility can be described by the flexibility of those bonds. This would be Fleury's rotational isomeric state model, or by some Kuhn lengths. We saw this in Muthu Kumar's lecture on molecular dynamics, or a persistence length, which is really the length you have to walk along the molecule until you have a new direction, which is disconnected from your original connection. The stiffness of the molecules hinders the rotational diffusion, so those molecules cannot rotate as freely, but they can translate very freely, at least in most cases. So that's where the lack of positional order comes. They're translating pretty fast, but they cannot rotate. They are easy to orient and flow, and they already have the extended chain conformation, which is advantageous for achieving extreme mechanical properties. And in fiber spinning, that's used for instance. But also, optical properties are very interesting because of those high degrees of orientation and maybe homogeneous orientation, which can be achieved in liquid crystal samples. In the next lecture, Mohan will talk about optical properties of those liquid crystal polymers. I only will talk about mechanical properties here in that system, in this lecture. On a larger scale, those molecules form some interesting morphology. Initially, one modeled the morphology as such, assuming that around a D vector, molecules are aligned like this in a domain which might be of micron size, and in a neighboring domain, the molecules might be aligned like this, and there's a discontinuity at the boundary. The picture of that model would be logs floating on a river and grouping up. However, the most, or actually I don't know of any liquid crystal which behaves like this. A more realistic model would be one where molecules align locally, and as you form regions like this, there will be disclinations where the D vector, see the D vector changes gradually across in this direction, but there are discontinuities in the D vector. Those boundaries actually don't exist, and we can describe this type of domain structure by a set of defects distributed in space. The characteristic length of the texture would be the distance between those disclinations. Locally, we would define a D vector as before. We would have also an order parameter around this D vector. The specific form of those disclinations can be adopt many different shapes here, can be of many different types. The typical structure would be a hairpin like this, where a direction of this type is changing into a direction of that type over a short distance. These lines are tangent to the D vector. Another disclination is defined as such, and there are many different possibilities. We would have to look at microscopic studies to look at the defects in polymeric liquids. In pneumatic systems of low molecular weight liquid crystal materials, a lot of those defects have been studied in the microscope, and you can find them in the literature. Those defects most often occur pairwise. They come together, and actually one has a strength of, say, plus 1/2, and other have a strength of minus 1/2. And if those two defects are approaching each other, then they are annihilating each other, and the defect is vanishing, and the overall density of defects is reduced. I took a pair of those defects and magnified them a little bit just to talk about the strength of disclination. We can take a pen, maybe I take this pen here, and align it tangentially to one of those. I just magnified the picture which you have on your thing. And now I'm rotating this. I'm rotating this pen. I'm describing a circle clockwise, and I always keep tangent position to the vector lines which I have here during this rotation. And you can see that after one rotation, this pin has rotated by minus 1/2 counterclockwise. So this defect has a strength of minus 1/2. Let's do it again for the next defect down here, which is counteracting here. I'm starting on this line here. This is a disclination line, and I'm describing a circle all around here while staying tangent. I'm staying tangent here, staying tangent, staying here, and then I keep rotating while coming back, and now I came back to the same disclination line, and you can see that by going clockwise around, this pin rotated, or this arrow rotated plus 1/2, and it has a disclination strength of 1/2. That's how those are defined. And there are disclinations which have a strength of 1 or 1.5 or higher order disclinations. Steve Hudson with Ned Thomas produced interesting structures on very thin films of liquid crystal polymers, and they were able to stain them by a crystallization method. And you can see the plus defects and the minus defects coming in pairs and being very closely, very densely spaced in that material. So imagine this occurring not only on a surface, but in 3 dimensions. Those disclination lines would come around, and maybe a plus line would come back as a minus line, would form a loop. This would be a disclination line in space in the bulk of your material. And this disclination line then can, as the two approach, shrinks to smaller and smaller regions, and then it would disappear. Or if you generate defects, you would go the other way around. There are many possibilities, and the study of those defects has advanced significantly, but we really would like to know more about those. They have a large effect on rheology, as you will be seeing, because we are talking about structure of a large scale, which will affect linear viscoelasticity at very, very low frequencies. We will introduce some long time constants in the relaxation time spectrum. And also will make the sample very sensitive to shear deformations, because we will break that structure in large deformations. So for rheology, that's very important. Excuse me, the time constant?
No, not constant. Sorry, the constant C.
The strength of the disclination?
No, that's S, right? So
Yes.
we have another parameter.
Oh, in Thomas's picture, the psi. Oh, let's see. Okay. It's this constant. It doesn't have any meaning in this discussion here in the moment. So we're talking about the strength mostly. That's the important part. I don't want to go into detail. Frank studied those defects in very much detail in Bristol, and the elasticity associated with that large superstructure is called Frank elasticity because of his work. And this is Frank elasticity as compared to the chain elasticity which we see in coiled polymers, in polymer melts, or in rubber molecules. So here we don't have molecules which can coil, so they don't have entropy elasticity in the classical sense. They have the elasticity due to the superstructure, which is a very interesting phenomenon rheologically, and I will show you an example about that. The ordering, the self-ordering of those molecules is associated with transitions, with classical transitions. The high temperature behavior is associated with isotropic structure. Molecules can move around very freely. They can rotate very freely at high temperature. So the system is disordered. As the temperature is decreased, the order is somewhat increased. We lose the rotational possibility of the molecules. We still have translational freedom in the molecule, and that's the pneumatic system which we are going to talk about. At lower temperatures, the system becomes smectic, where the chains cannot, they order further and they cannot move anymore. You have some additional position order, and there are several different smectic structures which might appear. And then at even lower temperatures, the material becomes a solid now. Those are intermediate structures between liquid and solid. They're called mesogens or mesogenic structures. Because of that, they're called mesophases. And now we would have a solid, which is crystal, where the molecules are on a lattice, on an ordered pattern. And at even lower temperature, the part which hasn't crystallized yet will vitrify, so the molecular motion is reduced. There are systems which directly go from an isotropic state to the glass, like a polystyrene, and there are systems which are liquid crystals which go from a isotropic to the pneumatic state and then to the glass. It would be pneumatic glasses. There are many examples. We have a system which skips the smectic state and goes from the pneumatic to the liquid crystal. In fact, for many liquid crystal polymers, this isotropic state is at such a high temperature that it's not accessible. The polymer would degrade before that. So we will have a system which doesn't have the isotropic state available. But I will also show a few examples where all of those states are available. The appearance of the mesophase depends on the molecular structure, on the stiffening of the molecules. The oldest thermotropic liquid crystal polymer was proposed by Jackson and Kufus, who realized that when putting mesogens in the backbone of a chain, which also had flexible spacers here, when putting those mesogens in here, they needed a certain amount of those mesogens, and the viscosity went down. And then if they put too much in that, the viscosity went up. We haven't even talked about rheology, but the viscosity is very low of those pneumatic systems. So very often the viscosity is used to discover or to detect the appearance of a pneumatic phase. So the viscosity goes down here. First, when adding those liquid crystal elements, those mesogens in the backbone, the chain the motion of the chain is hindered, but then in the pneumatic phase, motion is increased. And then again, when it gets very stiff, you cannot melt it anymore, and it doesn't move. You would have to use solvents to lower the viscosity. This example is a thermotropic liquid crystal. There are other systems where the chain is so stiff that we are not able to melt the system at reasonable temperatures. We have to add solvent to mobilize the molecules. If you take such a lyotropic liquid crystal, that's the name, lyotropic liquid crystal systems, and add more and more polymer to the solvent, you first increase the viscosity. As the pneumatic state appears, the viscosity drops. Again, we use viscosity to detect the appearance of a pneumatic phase. And then as you add more polymer, the hindrance of the molecules increases the viscosity, and additional things might be occurring. Most of the things I'm going to discuss today will deal with thermotropic liquid crystals and not with the lyotropic systems. Typical properties of those thermotropic liquid crystals are listed here. The viscosity is very low in the pneumatic state. You just saw that in some examples. The viscosity is very temperature dependent because you have those temperature-induced transitions. So you have to move to a certain temperature, and suddenly as a transition into the pneumatic state occurs, viscosity drops, and the viscosity, and you see that in those sudden changes. The material is very sensitive to strains. That comes from the superstructure, from the texture, in large scale texture in the material. Elasticity is fairly low. You can see that in extrudates well. When extruding a polyethylene through a die, it will increase its diameter tremendously at the exit, but a liquid crystal polymer maintains its shape, which really is an advantage when you process material into an extrudate of defined cross-section. You can control that much better. The normal stress difference in shear, the first normal stress difference, is negative in certain regions, a phenomenon which is not completely understood. Zero shear viscosity is not accessible because of those superstructures. You would have to go low rates of deformation, and we cannot do that in our rheometer. So in most cases, this zero shear viscosity is cut off. History is important, sample history, because of interesting crystallization phenomena and transitions which are delayed. There's some hysteresis effect in history. And in some cases, for instance, with surface anchoring, the molecules are ordered in a certain way near a surface. And then when you have a shear apparatus or rheological apparatus which uses very thin samples, you will have those surface effects dominating as compared to the bulk effects. And then the different apparatus will give you very different results. So rheology will be very interesting of those systems. Here I charted out the state we are in currently, increasing the chain length down here and making the molecules more stiff. We would have a low molecular weight material, which is Newtonian, if the chains are not don't have any aspect ratio, but if you have sufficiently long molecules and make them stiff, then a low molecular weight theory, Leslie Erickson theory, describes phenomena very nicely. Now, at higher molecular weight, the material becomes viscoelastic. Molecular dynamics theories of Rouse and Doyle-Edwards would be of interest. Or from experiments, we know that we have a very simple spectrum coming in to describe the monodisperse material. It's being cut off at the longest time, and glass would come in at short times. So experimentally, we know a lot of details, and from theory, much information is given. If the molecular weight is increased further, we could reach a spectrum like this, which has a cutoff time which is getting longer and longer. If the molecular weight distribution is broadened, say, by the chemical reaction, when making long molecules, you most likely have a broader distribution. And in the extreme, you see that in a gelation process where you go from a liquid to a solid in a cross-linking reaction. And at the gel point, again, we would know the spectrum. So there's some information available for flexible chains at different status of their molecular structure. But if we want to know the behavior of the liquid crystal polymer, which has high molecular weight and chain stiffness, then very little information is available. I will show a number of experimental results. Most of them are taken from industrial sample. It's called Vector A900 by Höchst Celanese. It consists of hydroxybenzoic acid, which has a very, very high melting temperature by itself. It has chain stiffness, so you could make stiff chains with that just by itself. It's copolymerized with hydroxynaphthoic acid, which has this kink in the molecule. So the molecules cannot pack as closely anymore in a copolymer structure here. That decreases the order and also decreases the melting temperature. So that has been done purposely. It's a well-designed molecule so the kink is put in to decrease order and to lower the melting temperature to make the material processable. We will use that material for a few studies. I will start with linear viscoelastic data. Those experiments have been done by Susan Guskey. The sample has a melting transition at about 285. So we want to study the behavior in the melt, go to very high temperature to melt the sample completely at first, and then go to a low temperature, in this case 5 Kelvin above the nominal melting transition, and perform conventional linear viscoelastic test startups, and just to see how this material is behaving. The sample is nicely stable when going through that type of procedure. The modulus has been measured, G prime, G double prime have been measured as a function of time, staying at one frequency of 5 radians per second and a constant strain amplitude. And you can see that their value changes in time somewhat. This is a 5% limit we were drawing. Beyond 40 minutes, the sample is probably changing. Something is happening with the sample. But at least for 40 minutes, we can deal within a 5% limit. The stability is not as nice as we are used to in thermotropic, in conventional polymeric liquids, but it's pretty nice. And when you look at data in the literature, stability has been a problem in many data. The sample has been unstable. If you perform experiments, say at 310, as we saw in the literature, even higher, the sample changes, and you have all kinds of additional phenomena coming in. Susan wanted to exclude that and performed experiments at low temperature because of that. She used the dynamic mechanical test, as discussed before. The duration of this period is the probing time, which corresponds with the size of the relaxing unit. We have very large units because of the texture in the vector material. Therefore, we have to go to very low frequency and see what the behavior is. All experiments have been done in the nematic state. Here's a sample, a data sample taken with a liquid crystal made by Bob Lenz here. Data out of Masuda's group in Kyoto. He looked at the temperature dependence of G prime, G double prime, and calculated the viscosity from that. You can see that in the nematic state, the viscosity goes down. As the temperature is increased, the polymer, the structure is becoming isotropic, is disordered, and there the molecular the molecules interact more and the viscosity increases. Because at that molecular weight in a disordered polymer, you have a much higher viscosity. So this is the difference between the nematic structure and the isotropic structure in viscosity and relaxation modulus. All the data we will take is down here. The transition to the isotropic is not accessible for the vector material, but I still wanted to show how the transition comes in that type of experiment. We do some experiments with liquid crystals where all of this is available, but let's just concentrate on the nematic state. We would like to have linear viscoelastic data in the nematic state, probing G prime, G double prime over several frequencies, and we would like to stay within the linear viscoelastic range. The strain has been increased while staying at a constant frequency. You can see that the modulus is not affected for a while, and then it goes down, and the breakpoint depends on frequency. The higher the frequency, the earlier the breakpoint comes. Somehow, the material doesn't have a characteristic strain. We were used to see a strain limitation for linear viscoelasticity when looking at flexible polymers like polyethylene or polystyrene. Here, another criterion comes in. Sue plotted the data versus the stress amplitude, and in fact, all data break down at about the same stress of, say, 2 × 10⁴ Pascal. If the stress exceeds that limit, somehow linear viscoelasticity is sacrificed. There you can see that a constitutive equation for those models, for those materials, will not necessarily have a strain limitation. It should have a stress which comes in for describing this material, describing the behavior. There certainly is a linear viscoelastic range, as you saw, and within that, we can determine G prime, G double prime in its full extent. You see typical data here, but you also see that at low frequencies, there's no terminal region. If we would have reached the terminal behavior, G prime would have a slope of 2 or a slope of 0, depending on being a solid or liquid. Solid would have slope 0, and slope 2 would be for liquid. So with this data, we don't even know whether it is a liquid or a solid. It's behaving in between, but that's no excuse. It's really the large-scale structure which we would have to probe at very, very low frequencies, and that's outside the window of our experimentation. Time temperature superposition has been performed somewhat. Sue took data up to 305 degrees C and then pushed them and extended the superimposed them, extend the window a little bit. But we cannot perform experiments over very wide temperature range. That's another reason why our data are so limited. We are really stuck to the actual frequency window of the rheometer and cannot extend this with any sophisticated tricks. The spectrum can be calculated from the data, typical relaxation times and moduli, but the data are truncated, and the spectrum will only apply to a truncated set. We want to use now the information to model some experiments and also compare the model predictions to actual data. We would put a sample into a shear rheometer, turn it on so that the shear rate is constant over a longer period of time, and observe the shear stress as it grows and levels off, reaches steady values, and the first normal stress difference as it goes through some transition and stays constant. And you will see that in some cases it stays negative, in other cases it will adopt a positive value. But that's the interesting part. We really would like to look at transitions like that. For polymer solutions, those transitions have been reported by Moldenas and Mewis. Here's a lyotropic system studied in startup. The system actually is quite complicated. It has a cholesteric structure, a helical structure, which I haven't defined in here. So at rest, it has a complicated structure, but as flow is imposed, the structure changes to a pneumatic behavior. So we could call this a pneumatic system. And you can see that the stress goes through some interesting oscillations. It can be scaled. When if you describe the startups as a function of strain, you can superimpose experiments performed in different stress levels or different strain levels to obtain this curve. And the question is, where does this oscillation come from? And I don't even want to start speculating on that. Wispon, 1980, described the startup of a thermotropic liquid crystal. The shear stress is proportional to the torque, so we can say this is somehow shear stress related, goes through initial peak, breakdown of structure, and the stress builds up again, and then it doesn't stay constant, it somehow goes through a second maximum. Very often this first maximum appears at about 1 or 2 shear units, and this in the order of 100 to 150 shear units. You need many, many shear units to reach a halfway steady condition in this experiment. For conventional polymers, a shear of 10 or 20 shear units would be sufficient to reach steady state. The first normal stress difference is given by the normal force in the rheometer. After some transition, it's showing, it's leveling off. It shows some interesting behavior, but it's, I don't know what's doing. There have been some experiments on measuring the normal stress difference in shear, in steady shear conditions. Very famous are the experiments by Kiss and Porter in 1980, who reported negative first normal stress difference. This is N1 plotted as a function of shear rate, and actually this is really minus N1 plotted here, and no, excuse me, this is plus N1 plotted here, this is minus N1 plotted here, and this is plus N1 plotted here. So at intermediate shear rates, the first normal stress difference suddenly becomes negative, which means that in a shearing experiment, the polymer tries to pull the plates together. The sample tries to shrink, while in a polyethylene or polystyrene, the sample tries to push the plates apart in a shearing experiment. That's completely opposite and wasn't what people expected. So Porter and Kiss were very careful about those experiments, and it was confirmed in many other laboratories also, but they knew what they were doing in here. Baird performed similar experiments on a thermotropic liquid crystal, so that's a polymer melt, and he found negative shear stresses at low rates and positive, found negative N1 at low shear rates and positive N1 at higher shear rates. And that's basically what we are also finding, and we try to correlate this in an overall picture. Susan calculated the spectrum of the material, and now she performed some startup experiments at constant shear rate, which were ranging from 0.01 to 1 seconds to the minus 1, and this is the transient viscosity. You can see that the viscosity is very, very shear rate dependent in all experiments. You also see a transition at about 2 shear units where the sample structure breaks down, here it levels off, and then it has this going down and coming up. Maybe at higher shear rates we would see a more extreme transition. The short time behavior can be modeled with a linear viscoelastic spectrum because the strain is still small. So for the first 2 shear units, we would expect some agreement in the data. Here is the calculated startup of the viscosity divided here by, compared to the experimental values. The agreement, I think, is pretty good using truncated data. If we would have dynamic mechanical data over a wider range, we would expect more of an agreement. But initially has pretty much the same features. Could be nicer if you have a more complete spectrum of relaxation times. You can do you can do better modeling. Interesting is the startup of the first normal stress difference. If the shear rate is low, the stress first goes through some maximum, some positive values, and then becomes negative, and it stays constant. Susan managed to find the shear rate which gives us the zero normal stress difference at long times. This would be 0.5 seconds to the minus 1. And at higher shear rates, she has a positive normal stress. But the basic feature of basic structure of this curve is always the same, only that it gives negative values and positive values here. Has a very interesting transient, which we would like to learn more about. We also would like to know whether it is real, whether these negative normal stresses are real. So Susan stopped the rheometer and observed the stress relaxing, in this case the first normal stress relaxing, and indeed it approached the zero line after a while. So it's not a drifting zero which gives us artificial negative values. And then she started the flow again, and the same startup curve comes in a second time, and she reaches about the same level down here. So the transducer stayed fairly stable, and also our sample is okay at those short times. So this was our confirmation that the first normal stress differences were really negative. One problem in those experiments is that you have to use cone and plate because the strain is very large. You want to expose your material to a homogeneous deformation. And the cone and plate geometry is fixed. You have to have a very specific setting in your rheometer so that the cone is just touching the plate, or the tip of the cone, the imaginary tip is touching the plate. With the high temperatures of 280 to 300 or higher, you have to deal with thermal expansion of the rheometer. And it's very hard to adjust the gap setting at temperature gradients like that. So that was also a difficult part of the experiment which had to be mastered before the data became reasonable. We analyzed the data in terms of the spectrum. You can see that the simulation is in pretty good agreement with this initial hump in the data, the initial startup, and then at larger times everything becomes nonlinear. And the steady state values, the values of the normal stress difference after long times, would give principally the same picture as you saw coming from Baird's laboratory. A negative first normal stress difference at low rates, a zero value at 0.5 seconds to the minus 1. So it's not a singularity here. We really know where this is zero. And then a positive value in one at higher rates, at higher shear rates. And this could not be modeled with linear viscoelastic data. We would not expect that. The step strain experiment would give us stress relaxation, would have given us the relaxation modulus. This has been measured in step strains of 0.1 up to 5. You can see the different relaxation behavior here. And again, the simulation comes close, but it is not as nice as we are used to see that in conventional polymer melts. Conventional polymer melts are also modeled by the so-called Cox-Merz relation, where the dynamic viscosity is reproducing the steady shear viscosity. It doesn't hold for liquid crystal polymers, which is well known. The steady shear viscosity is in the vicinity of the dynamic viscosity, but it has a different slope. So somewhat, if you would operate out here, you would say there's no agreement at all. It's always easy to take the crossover point and say there's agreement. It's really a different structure in those two different curves. The viscosity behavior of that type is well known, has been reported in the literature quite often. Here's some data of Kalika. He also found, he didn't find a zero shear viscosity in that system. It's basically a power law behavior over the entire range. In the literature, there were many proposals of this type of viscosity curve, especially materials with structure, were said that they don't have only a zero shear viscosity, but that at very low rates, they would have an upturn in the viscosity curve. And the same model has been proposed for liquid crystal polymers. it's not clear whether we are operating in this upper region or in this lower region. So for the thermotropic systems, it's really not completely settled whether this viscosity function even applies. So in summary here, the linear viscoelastic behavior is found at very low strains and low stress levels. The stress level indeed has to be below 2 times 10 to the 4 Pascal, then linear viscoelasticity is satisfied. In startup experiments at low, or at some lower shear rates, the stress will never be very high. But we will achieve very large strains, and it turns out that as soon as the strain exceeds about 2 shear units, then the material becomes nonlinear. So we have 2 criteria now. For linear viscoelasticity, the strain has to be below this stress, or it has, and in addition, has to stay below that strain. Now, in dynamic mechanical experiments, we always stayed below 2. That was satisfied automatically, but we had to satisfy the stress level. The discrete spectrum has been determined, but it's a truncated spectrum. No zero shear viscosity can be seen, and a negative and a positive first normal stress difference is found, which is different from solution, because in solutions you have positive first normal stress difference at very low rates. You have an intermediate, at intermediate shear rate you have a negative N1, and then you have a positive N1. So this initial region is somewhat missing. Let's go to a completely different experiment, and then that would finish up the rheology. The large strain behavior in extension is also very interesting. We exposed the sample to equibiaxial extension by lubricating the surface of the squeezing apparatus. This experiment can be performed at very high temperatures, this lubricated squeezing experiment. It has been performed by Lynn here, and we worked with Lisa in Mainz on the microscopy, on the wax scattering to look at the morphology. So a sample has been produced like this and has been quenched, and then wax pattern will show that molecules are somewhat in this plane here, but they are not sticking out of the plane. So a wax pattern taken with an incident beam from the top will show isotropic pictures, and a wax pattern taken from the side will show those bundles being aligned within the planes, and it will show those reflections. And here are the pictures taken. The picture on the top here, that's taken from the side. You see that the molecular chains, the bundles are somewhat in here in that plane, and you see the reflections. And this is the top view where the bundles are randomly distributed in any direction. So that's something we expect, but we couldn't claim that the material is highly ordered because the molecules cannot bundle up. They really push down like the sticks in a Mikado game. Actually, I don't know whether this is the name in English. So you have like having many sticks piled on top of each other, and you're pushing them down into the plane before they are forming some interesting structure before. Now, those molecules, those semi-rigid molecules, would not stay in that push-down state if you give them the freedom to move. So we took the samples and heated them up again. This was the initial size of the sample H0. After stretching, the sample was thin, squished down to H1, and then it was heated up again to 300 degrees C, and it could recover. And you can see that the recovery, which is given by H2 over H0, if this is equal to 1, then we would have complete recovery. But you can see that in some cases where we squish the sample down to half its thickness, it recovers to 95% of its original height, or here it recovers to 70% of its original height. The material is highly elastic, and this is an elasticity which comes out of the superstructure of this material. It's so-called frank elasticity of the material. It's not the entropic elasticity which we would expect. And this type of elasticity would would affect the fiber blowing behavior or blow molding, film blowing behavior or blow molding behavior when you produce planar objects with liquid crystal material. So this is how our sample looked after squeezing it. It was very flat, and from this flat piece, a small sample had been taken, and then it was exposed to different temperatures. Depending on history, this sample shrunk to this dimension or to any of those. And in some cases, it shrunk down to nearly its original thickness. So at this point, I would like to break and continue with the thermal history of the material. Somehow rheology is very dependent on the thermal history, and we have to discuss that in greater detail. Is the speed okay? University of Massachusetts at Amherst. Chemical Engineering 757, lecture 23B. The transitions determine very much the rheological behavior, and those transitions are time dependent. There's some history involved. Because of reduced molecular mobility, we have to account for those long time phenomena, and I want to show you a few of those. The polymer we will use is again the Vector A900, which has about 73% HBA and 27% HNA. Or was it? Yeah, I think so. Now, the transitions can be shown in a DSC diagram. When you heat up the sample, would be the first heating cycle. You do this once or twice. So you heat up the sample. The melting occurs over a very broad temperature range. The temperature of highest melting rate we would call the melting temperature, nominal melting temperature. And beyond that, the material is a liquid. If you heat further, the melting will be completed, and then during cooling, the material stays a liquid for quite a while. It will stay in a supercooled state. You could probe the material at temperatures much below TM. It will see liquid behavior, and then if you go deep enough into quenching deep enough, you will find the solidification. We'll see the solid behavior coming in. We will look at a few data in the beginning where we go to a very low temperature, we heat up the sample, and then we look at the rheology in the supercooled state. The material will not stay solid in that supercooled state for a very long time. We have performed, those are data from Yegang Lin. He has performed experiments at many different temperatures from 275 down to 255 and observed the growth of G prime and G double prime. The moduli increased by several orders of magnitude. This is on a log scale, so the sample goes from a liquid state to the solid state. It needs a while for the crystallization to start. There's a nucleation process. The rate increases as the nuclei are there, and then it saturates as the molecules cannot move around freely anymore when the degree of crystallinity is high enough. The characteristic time of that experiment is different. It's very, very long if we supercool only by 10 Kelvin, or it's very short if we supercool to 255. This is plotted down here. So this characteristic time as a function of temperature, here a more beautiful plot of the same function here. This time, this characteristic time, is an important processing parameter. We could, for instance, cool the liquid crystal melt after having, well, we first go to high temperature, but then we would cool it down, say, to a temperature of 255 or 260, and then the solidification occurs in 1 or 2 minutes, in a very short times. During that time, we could blow films or blow bottles and make something out of the shape they melt and quench in the flow-induced structure. So processing in the supercooled state with this type of rheological experiment proceeding will be very successful, and we will know the time scale. We can tailor the time scale by changing the chemistry and doing rheology in an experiment like that. Very interesting is also the rheology just above the nominal melting temperature. We would melt our sample, but because it's a broad melting transition, we will not melt the sample completely if we don't heat to a very high temperature. If we stay at 285 up to 300 degrees C, as you will see, the sample shows some very interesting behavior. Now this figure is very crowded, and I wanted to pick just 2 curves. We have G prime and G double prime at 290 degrees measured as a function of time, measured at a constant frequency at 1 per second. So at 1 frequency, we stay, and we see that G prime and G double prime increase by several orders of magnitude. This would be 1 order, 2 orders, and up to 3 orders of magnitude. So the material had been a liquid initially, and while we study it in the rheometer, it goes from a liquid state to a solid state. It's somewhat not stable, and rheology is in deep trouble, because the first rule in rheology is that you have a stable sample. And so we study this change of G prime, G double prime for a while, and then we heat the sample from 290, this up here, it was done at 290 degrees C, we heat it up to 320, and then go back to 290, and you can see that the whole phenomenon is reversible. We go down to the original modulus, and in fact the process is much slower this time than before. Let me start out with the hypothesis for this process. We assume that a partial melting here, when you go back to the DSC, the broad melting distribution here would require heating to very high temperature, but at this temperature above the basic peak here, we might have melted 99% of the material. But there's a small fraction of polymer which has higher order and has higher melting temperature, and that will stay solid in the system. And this will act as a nucleus. So in this process, nuclei are already present. The crystallization process starts very quickly. We say that this is a recrystallization process of this material. So it goes fairly fast because the nuclei are present. And secondly, the nuclei are of high order, and every addition to that nuclei, every growth will be associated with a structure of high order. So the new material which we generate in this process has a much increased melting temperature. The melting temperature, in fact, increases by about 30 Kelvin in this recrystallization, and the order is much higher. There's a new ring coming in with the wax pattern. But let's move step by step. We studied this process by heating the sample barely above the melting temperature, but that's the parameter of the experiment. It is 285, 290, and 295. You can see that the process is faster at lower temperatures. If we don't melt the sample too much, it's a faster process. This is an indication that we really deal with a physical phenomenon. If those phenomena would be induced by chemistry, then the rate of change would be higher at higher temperatures. But in this case, the rate of change goes down. In fact, at 295, it vanishes. And if we would deal with a transesterification process, for instance, which may occur in systems like that, then the phenomenon would be reversed temperature-wise. So it's the fastest at lowest temperature. And if we go to 300 degrees C, not much is happening to the system anymore. We can preheat the sample now for a short time and melt part of that structure. See, our hypothesis is partial melting, leaving some nuclei in the system, and then going to some new temperature, 285, and observe the crystallization. And you can see if we heat up to 300 degrees, if we go to a very high temperature, nothing is occurring. If we go to 295, a little bit is occurring. But if we stay below that, let's say 290 and below, the crystallization is very, very strong. So melting out of the structure can occur at very short time when going to a high temperature for just quickly and then cooling down. That's the history which was used by Sugaski to do rheology, to obtain a stable sample. She melted out the structure and then she stayed under stable conditions, and that was an advantage for that experiment. However, we would like to generate samples with a very high melting temperature, and this can be achieved by melting the sample partially to 290 degrees. We know that only a small fraction is left in the solid state. But then we supercool the sample. We go to some lower temperature, and this temperature is our parameter now. It might be above Tm or below Tm. In fact, we can now go down to low temperatures. We can, this is the recrystallization at 290 degrees using rheology as a tool to study crystallization. By the way, that's an interesting way of using rheology. Very few people have used rheology to study crystallization in situ. You can do that experiment very easily, get lots of information, and then do some additional experiments to learn more about the crystal structure. So we look at the rate of crystallization through rheology. It's fairly slow at 290, but in a supercooled state, when we go down to 275, the recrystallization occurs very quickly. In the previous data I showed on supercooling, you saw that there was a slow period of crystallization initially, a nucleation period. In this case, the nuclei had been presented already because of this partial melting which we applied and leaving some nuclei in the system. And on those nuclei, the crystallization started. The modulus goes up by 3 orders very, very quickly. And the new structures now, we did lots of those X-ray pictures and DSC pictures on the system. So I'm showing you the one example here of the DSC. The freshly molded sample had a transition at about 285. But the recrystallized sample had a much higher melting temperature. If you do that at very high speed, the order will not be as high, so the new melting temperature will not be extremely high, but it's still above 300 degrees C. While if you do things more slowly, you get more perfect order, and you get higher melting temperatures coming in. There's an additional spacing with this new order. There's an initial spacing in the wax pattern associated with it's 3.8 angstrom spacing, and that's associated with whatever order is coming in. It's the same spacing as one of the components, so it's not completely clear what's happening. Note that in this experiment, which we just talked, the melting temperature by itself has no specific meaning anymore. We couldn't talk about supercooling or things like that, because the recrystallization curves, here let me show those again, the recrystallization curves are about the same at 290, at 285, 280, 275. There's a gradual transition from one to the other, and the previous melting temperature has no significance because it's associated with a different order and a different type of crystal. which we overcome by choosing a different by choosing this prehistory. We could change this phenomenon further by annealing the sample in the solid state. So even before doing rheology, we would anneal the sample and increase the molecular order in that system. This phenomenon has been studied extensively by Blackwell and by Windle, who looked at the order in those materials and produced very highly ordered liquid crystal samples with fiber spinning and annealing. And you can see that in the X-ray structures. So annealing will improve. Annealing in the solid state will improve the order and will change the melting temperature of the system. The parameter of the annealing in the solid state is the time of annealing, and it is the temperature of the annealing. So that will be done first. And then we go to a temperature slightly above the melting temperature, 290, and try to induce a lot of this highly ordered structure. Now, by performing this annealing, we can increase the rate of crystallization, certainly. But the effect is not very large. The effect actually is reversed in some cases because the annealing in the solid state might introduce such a large fraction of high-ordered region in the system that the molecules are not mobile anymore, and they are not able to form the highly ordered structure which we are trying to achieve. So annealing in the solid state for will decrease the growth of the modulus and the growth rate of the modulus, and is not advantageous in this case. So the fastest way of getting order would be melting, say, to 290 degrees, about 5 Kelvin above the nominal melting temperature of the liquid crystal, and then supercooling to some low temperature. You have a high rate of crystallization and the nuclei of high order, and you obtain a highly ordered system, which is very, very nice. So in summary, the temperature history is very, very important here. Talked about rheology before. Temperature history shows melting over a very wide temperature range. The partial melting will result in a recrystallization and further in a structure which has a very high melting temperature. And that type of structure is attempted in processing. The supercooling will increase the formation of those highly ordered regions. If we melt the sample completely, we have first nucleation and then growth. Or if we if we only partially melt the sample, we already have the nuclei and can we see a faster growth of the crystal structure, and the moduli, the solidification occurs faster. So the temperature history in the liquid crystal polymer has a large effect on the final morphology of the part which you're producing. And that's different from the conventional processing of polymeric materials. You will not be able to sell a liquid crystal polymer to some processor who doesn't know about the material. So that's one reason why this polymer has not been used extensively in many applications. Somehow also the relations between temperature history and structure and flow and structure are incompletely understood. So those are regions of area of current research. And that's, for instance, an area where we combine optical studies with the mechanical studies to learn about the relation between structural phenomena and mechanical properties. The transestrification, which is found in that system, doesn't seem to play a role at the time scale and temperatures we are performing the rheology. There certainly are phenomena due to transestrification. For instance, even if you store the sample at room temperature for a year, there are some slow changes occurring in this material. And that might be due to transestrification. I don't know in detail whether this is true. We looked at the behavior of a blend of two liquid crystal polymers. So we blended homopolymers, or we're blending liquid crystal polymers with homopolymers. Why not blending two liquid crystal polymers? Yigang did that study, Yigang Lin, and he used the vector material with 73% HBA and 27% HNA. And he also used the Tennessee Eastman material, which had 60% of the mesogen units in there. It actually is a two-phase material. The mesogen and the PET phase separate in that system. The PET forms an isotropic region and the PHB a nematic region in that system. It has been mixed before performing the rheology. If there's transestrification, then certainly those molecules would be cut and recombined, and we will see a mixture of the properties in a fairly short time. So we looked at the DSC of the material after having this material exposed to some higher temperature for a while, and you can see that the transitions, which occur at very different temperatures, the transitions change slightly here. We have 100% of, no, we're going from one polymer to the other. And I should be looking up which polymer we have first. Trouble. Look it up. I gave the reference. So So those are cooling curves. I would assume that this is the cooling behavior of the vector material at cooling of 20 Kelvin. We know that it will solidify at about 255, and this will be the cooling transition of the Tennessee Eastman material. So this is the curve all vector, and this is the curve all Tennessee Eastman. The peak, the strength of the peak, or the area under the peak, now depends on the content. If the vector content goes from 0 to 100%, the peak associated goes from 0 to its full value, and the peak of the Tennessee Eastman material goes from its full value to a 0 value. Now, those transitions are so linear that we assume that there is no mixing between the two components. We're talking about an additivity of the two components coming into play here. So no transestrification is occurring in this material. It is staying clearly phase separated. The rheology reflects that, or well, let's see how the rheology behaves. This is linear viscoelasticity, which is possible at low rates. This is 100% of the vector material. So again, the first number indicates the vector here. And you saw that also already from Sugaski's data. Now, the spectrum of the Tennessee Eastman material is much lower. Maybe I should superimpose that. It's more liquid-like. Actually, the liquid range is accessible in the system. They are drawn on the same scale. You can see that at low frequencies, somehow the vector material levels off and the Tennessee Eastman goes down. So it's more liquid-like, and the viscosity will be somewhere in between. You somehow can mobilize the vector material by adding a little bit of the Tennessee Eastman material to that. This is, for instance, intermediate composition. There's 10% of the Tennessee Eastman with 90% vector. And you can see already that the terminal zone has been changed. It's completely different, and this will affect the processing. The viscosity of the material, where we have 100% vector on this side and 0% there, the viscosity is not described by a linear linear interpolation, the viscosity drops significantly to 1/4 of its value when we're adding about 10% of the Tennessee Eastman material. So you can add one liquid crystal to a second liquid crystal material to lower the viscosity even lower, and this way get an interesting injection molding grade, which has probably interesting properties because you have an all liquid crystal polymeric material, but having this very, very low viscosity. Negative normal stresses have been found in that system in the same way as before. So, and the low viscosity and the lack of transesterification are the most interesting phenomena. Let me mention quickly, just in the last minute, a few things about processing. The flow-induced order depends very much on the type of processing. One-dimensional processes like fiber spinning will produce very high moduli, high tensile strength, and they will really enhance everything we get from the molecules, because the molecules will align along that structure, and we're probing the backbone properties of that system having extended chains. In a two-dimensional processing, like in film blowing, blow molding, or in the squeezing experiments which you saw, we have little information about the usefulness of those materials, but you saw that the molecules don't know where to go in a planar structure as compared to the fiber. Much application has been found in injection molding. Three-dimensional objects have been produced because of the low viscosity of this material. You can have very intricate molds being filled with that system. The injection molding is very interesting. I just made a list of the positive aspects of injection molding. The low viscosity helps mold filling, which is very important for specific, very thin-walled parts in computer or in connector applications. So easy to fill complex shapes. The flow-induced anisotropy is not desirable in all cases. We're not going for mechanical strength, as you will see in a moment. Weld interfaces occur quite frequently in blow molding because the mold, which has maybe very complicated shape, might be fed from two parts. And as the two fronts of melt approach, they will get into contact, and then they're forming an interface of highly oriented molecules. And the strength in this range is very, very low. The biggest problem in this application is really the occurrence of those weld interfaces. And you want to control where they are by designing your mold so that you might place them somewhere where they are not probed by any mechanical stress. So mold filling is okay because of its low viscosity. Interesting is then, it's even more interesting in this application, is this low shrinkage behavior. The low coefficient of thermal expansion allows to reproduce complicated shapes of this mold. The parts warp very little, so they maintain their geometry. The release is very easy. The parts don't stick to the surface. And due to the high temperatures, we are dealing with very high cycle times in these in the injection molding. The parts have very good solvent resistance. They don't swell, which is important for instance, connectors in a computer where you put more and more wires closer and closer together. So that's where they find an application. And a computer in a moist environment should not suddenly have different signals or have some cross-talking because of lack of insulation. So the good resistance to solvent or to water is good. The modulus is high, which is an additional, which is interesting for liquid. The low flammability is another application which makes liquid crystal interesting for transportation applications. And then there are all those optical properties which are coming in, which we will see in the next lecture. So that's also gives rise to a whole range of interesting morphologies, interesting properties, interesting applications. So that's just a short outlook on processing of liquid crystal polymers. We we are in the beginning, I would say, in understanding the liquid crystal melt rheology. The research has been started in the 70s. Initial work has been done by Wispren at Celanese, very nice papers. You see them in the list of publications. Dan Baer did some pioneering work, but there's still lots to do, and it's a real opportunity for you as a new generation coming in and taking the field over. Thank you. So, that's the German.